So we're going to make a little context switch to memory. Although we've talked about memory, memory was always a part of what we've discussed, even though we never really deeply went into memory, except for the design of the sequential logic and some memory cells that we briefly discussed. But now we're going to go into memory as much as possible in this course, but we're not going to be able to do full justice to the memory system, because this is really where the bottlenecks lie today in existing systems, and it requires its own course. And our computer architecture course is actually dedicated a lot to the memory system as well as the interconnects. That's the master's level course. And we will cover a lot in the bachelor's seminar also. But in the remaining lectures, we'll give you a relatively short introduction into what the memory is about. So these are the readings that I'm going to assign. Basically, Harris and Harris, chapters 8.1 through 8.3, does an okay job covering memory, not that great, but you can take a look at it. And this is for refreshing Pat and Patel. You actually read this last part. And this is an early cache paper by Morris Wilks that talks about, that introduces caches. It's not the earliest paper, but it is an insightful paper that introduces memory. It's only 3 pages, but it's recommended, it's not required. So if you look at a computing system, this is John von Neumann over here, and that's the paper that we had referenced before, where he and colleagues introduced the von Neumann architecture. It has 3 key components. This is not actually limited to von Neumann architecture, but von Neumann architecture has become almost synonymous with these. Basically, you have computation units, you have communication units, and you have storage and memory units. We've talked about computation a lot. Systolic arrays are a very good example of computation, even though they integrate memory in it. Now we're going to talk a lot about memory. There's also a communication, which is the interconnect, which exists both in the computation unit as well as the memory unit. It's really about the interconnect, actually, how you supply the data, how you wire the buses, how you design that interconnect. It's really important. So it has been part of our conversations, but we never have done a formal treatment of what that communication substrate could be. It could be a bus, it could be a network, it could be a hypercube, for example. It could be an n-dimensional hypercube. We're not going to do that. I don't think we'll have time in this course, but this is a really important part of the architecture as well. So this is another view of what is a computer. You have processing, which we've covered a lot. You have memory, which we've covered mainly tangentially, and I/O, which we have not covered that much, and we're probably not going to cover as much right now. So let's look at memory. So this is the programmer's view of memory, right? As a programmer, memory is a black box. In this case, it's a white box. You store data to it and load data from it, right? That's it. It's a dumb box, if you will. Maybe that should change, but let's look at what's in that dumb box first. And we're going to start with an abstraction, which we may go back into later. What the programmer sees in general purpose systems today, that's not true for all systems, but in general purpose systems today, is virtual memory. Now, what does that mean? This is an illusion or abstraction provided to the programmer. The programmer can assume that the memory is infinite, or almost infinite. The reality is, physical memory size is much smaller than what the programmer assumes in most real systems. For example, you can have hundreds of programs. They all assume that they have the memory for themselves. And if you actually multiply the number of programs with the amount of memory they assume, you're going to find out that the physical memory size on your machine is much smaller than that assumption, right? For example, each program can assume that they have 4 gigabytes of memory, and you have hundreds of programs, and you have 400 gigabytes. The memory on my computer is about 4 gigabytes. Clearly, I don't have 400 gigabytes, right? And these programs still run without any problem. So that abstraction is really powerful, and that's the virtual memory abstraction. So despite this reality, somebody ensures that that abstraction holds and works correctly, and that somebody is the system software and the hardware cooperatively. They map virtual memory addresses to physical memory and ensure that the data is in physical memory when it's needed by the program. And that's the virtual to physical translation that happens. Programmer assumes virtual memory, and the system automatically manages the physical memory transparently to the programmer. The big upside of this idea is programmer doesn't need to know the size of the physical memory, nor does he or she need to manage the memory at all, right? A small physical memory can appear as a huge one to the programmer without the programmer knowing it, and as a result, life is easier for the programmer, right? If you had to care about how much memory you had when you wrote your program, you would be in great trouble. That's what people did in the past. In the 1960s, actually virtual memory is a concept that was developed in the 1950s in the Atlas computer initially. But it was not adopted for a long time in general purpose systems. If you were writing a program in 1960s, you would be managing, oh, is my data in physical memory? And you would be doing overlays and ensuring that your data is brought to physical memory before you could process it, right? That sounds terrible, right? You have a lot of things to worry about, and one more thing to worry about is how big is the size of the physical memory on this machine? Because your program can run on many machines, and they may all have different sizes of physical memory also, right? Virtual memory enables cross-platform portability of the code as well. So that's the big upside. Life is easier. But the big downside is life is more complex for someone else, and that someone else is you as an architect or a system software designer, right? You need to ensure that this works. And this is a very classic example of the programmer-architect trade-off. And we've seen some of these trade-offs earlier, but we've seen some of these trade-offs actually in VLIW machines, right? In VLIW machines, programmer's life is harder, architect's life is easier. In out-of-order execution machines, programmer's life is easier. They don't need to figure out the independence of the instructions. Architect's life is harder. You need to design that complicated out-of-order machine. This is one example. You could say, I want to make programmer's life easier. Then you need to design this abstraction and make sure it works correctly. Virtual memory system works correctly. Or you could punt and say, I don't care about the programmer. Programmers should manage their physical memory themselves. Then your life is easier as an architect or a system software designer, but the programmer suffers. And in general, ideas that have made programmers' lives easier have become more successful than ideas that have not made programmers' lives easier. So I would suggest taking into account the programmers' lives when you actually design systems. Okay, so that's our abstraction. We may actually talk about virtual memory later if we have enough lectures. Have you actually covered this in another class? Not yet? Okay, you will definitely cover it in the systems programming class. And I will try to squeeze it in since we haven't covered in some other class. Okay, but let's assume that we are going to be physical for now, because you need to know the basis of physical memory to understand virtual memory better. But always think that a programmer sees the virtual memory. Basically, you need a larger level of storage to manage a small amount of physical memory automatically. If you're designing the virtual memory system, you have only physical memory, and how do you ensure that the programmer sees an abstraction? Well, you cannot just assume that all your data is in physical memory, because clearly all your data of all your 400 gigabytes cannot be in your 4 gigabyte physical memory. There has to be some other place where you store the data, and that place is the hard disk, for example. It's called a backing store. So physical memory needs to have a backing store so that you can actually give the illusion of an infinite physical memory. And when the programmer requests something that is not in physical memory, you automatically bring the data from that backing store into the physical memory. That's the idea. That's how you manage the virtual memory abstraction. So we're going to assume that you have a disk, but we will start with the physical memory system. And we're going to, for now, ignore the virtual to physical indirection. We're going to assume everything is physical. And virtual memory adds a layer of indirection on top of it that requires translation of virtual to physical addresses. So we will get back to it later if time permits, and I will try to prioritize it. But let's talk about idealism a little bit. I'm going to talk about this idealism, but I'm going to get back to this idealism later on, probably in tomorrow's lecture. But whenever you're designing a system, it's always good to think ideal. That's how you can improve things. Remember, we always ask the question, can we do better, right? So what are the limits of can we do better? This is my little picture of what a system looks like. Very limited. You have the pipeline that does the instruction execution. It can employ any of the techniques that we've discussed, including systolic arrays, right? And yeah, you need to supply instructions to it. You need to supply data to it. Ideally, you want no pipeline stalls here, right? You want perfect data flow. When the data value is available, it gets to the right place. Zero cycle interconnect, no latency for operand communication, enough functional units to support the parallelism, and zero latency compute. That sounds beautiful, right? And we should always strive for that ideal. It may be hard to get. And we kind of strive for that ideal. And I don't even look at the energy requirements, reliability requirements, ... over here. If you want instruction supply, we talked about the instruction supply also. You want to supply instructions quickly. You want to have high capacity. You want to have zero cost clearly. And you have to have perfect control flow. We focused a lot on the perfect control flow part of it, right? How do you actually try to predict your control flow? Because what you're supplying over here is not in the order that you need them, then you have a problem. And the data supply is very similar to the instruction supply. You want fast access, zero latency access, infinite capacity, and infinite bandwidth, so that you can actually support many, many instructions, many data. And we've tried to do that with banking, not the financial form of banking, but banking a memory, right? So that we can get high bandwidth, right? One data word per cycle. And you want zero cost also. So we're going to look at especially the data supply aspects of memory. But memory is greater than that, actually. Instruction supply contains memory also clearly. Memory is very integrated into the pipeline with the caches. And we're going to talk about the concept of caching also. But let's do a first quick overview of memory arrays and how they're designed. Because all memory looks the same, but they may be designed based on different technology. Let's take a look at what that looks the same means. So we've seen some things over here. Basically, how can we store data? Flip-flops or latches we've seen. They're very fast, parallel access. They're very expensive compared to these things that we're going to see. Basically, 1 bit costs tens of transistors. That's expensive, and you cannot afford it in many places. Static RAM, SRAM, we will see that soon. It's relatively fast, only 1 data word at a time. That's the downside. It's also expensive. 1 bit costs about 6 transistors. There are different variants of SRAM, but 6T variant is actually used in many systems today. Dynamic RAM, DRAM, we actually talked a lot about DRAM, but we're going to talk a little bit more. It's slower, so you can see there are a lot of reds over here. You get 1 data word at a time. Reading destroys the content. You need special process for manufacturing this because you rely on a capacitor. But you do all of this, you tolerate all of these reds because there's a green over there. And that green is it's cheap. Cheap means 1 bit costs only 1 transistor plus 1 capacitor. And you can pack a lot of data into main memory. And as a result, this is the dominant technology that we use for main memory, right? Even though it has all these reds compared to these 2 other ones, right? And we have a lot of data. We want to pack a lot more data into the systems. That's why DRAM is going to be even more important. And I will say that even though the memory technology companies today are not really doing a lot of innovation, they're being very, very successful. That's really kind of a weird thing, right? They're not extremely innovative as long as companies go, because they're not really disrupting. They're really doing business as usual, as they've known it for 50 years. But they're still extremely successful because there's a huge demand for main memory. Now, that doesn't mean that they're always going to be successful, because if they don't innovate, somebody will at some point come and disrupt their system, and they will be out of business. Now, if they're listening, they can heed this, perhaps. This is really true, actually. This is called the innovator's dilemma. There's a book about it. And if you're too much ingrained in business as usual, you may be making a lot of money at the time, but if you don't innovate, once that money-making business path goes away for whatever reason, and that whatever reason can be someone came up with a really disruptive technology that actually has better characteristics than this, and they can disrupt all of your business. That's why this is really important for even the big companies to innovate. Once they lose that innovation, they will have a big problem. I don't care, I don't make money for them, so it's their problem, right, in the end. But if you're going to make money, and if you're going to form your companies, heed that. And I would recommend that you read that book called Innovator's Dilemma. Okay, there are other, and one reason this might be disrupted is because there are other storage technologies that may actually disrupt things. Everything over here, actually. So these are the ones that already exist: flash memory, hard disk, and tape. They're much slower. Access takes a long time. They're non-volatile. So they have a green over here compared to DRAM. And if you have a technology that's non-volatile and maybe similar to DRAM, maybe you'll win, right? Okay, but these are actually very, very cheap. Flash memory is cheaper than DRAM. Hard disk is cheaper than flash memory. Tape is cheaper than hard disk. And all of these are used in existing systems. There are no transistors directly involved. We're not going to cover these parts. Although flash memory is fascinating, and we do a lot of research on flash memory. And that's a technology that's not going to go away, I believe. It's going to be even more successful into the future. And we may talk about, we're not going to talk about it, but in a slide later, I may talk about other non-volatile technologies like phase change memory that have characteristics that are perhaps better than flash memory and that are getting closer to DRAM as well. So there's a big landscape in how we store the data. It doesn't matter what technology you use, memory always looks like this. Basically, your goal is to efficiently store large amounts of data, and as a result, you design these arrays. And this abstraction at the high level holds, and internally, the memory looks like smaller subarrays. So if you, it's like snowflakes, if you will. If you look outside, it looks like an array. If you look inside, it's an array of arrays. If you go into the array, it's an array of arrays also. So basically, at all levels, you see arrays, because that's how you design regular and large systems. So basically, at this abstraction level, you have a memory array that stores data, you have an address selection logic, selects one row of the array, and you have a readout circuitry that reads data out. So you have m-bit address, and you read out m bits of data. So an m-bit value can be read or written at each unique m-bit address. All values can be accessed, but only m bits at a time. And that enables cheap, right? If you were able to access everything at a time, these buses would be large, and these address buses, you need to supply multiple addresses. As a result, your pins, you would have a lot of pins into this chip, and that would be very expensive. So basically, access restriction allows both more compact organization as well as less pins. Okay, so memory arrays, again, look like this. This is basically, you have a two-dimensional array of bit cells. Each bit cell stores 1 bit. An array with n address bits and m data bits has 2 to the n rows and m columns, as you can see over here. So depth is the number of rows, width is the number of columns. These are obvious, hopefully. Array size is depth times width. And this is an example of an array that has 4 addresses and has 3-bit addressability, or what you can read. And I'm not going to go through this. Clearly, we've done this before, right? You supply the address to, you supply an address and you get the data. Okay. And this is a larger memory array. You may build it this way, or you may build it, unfortunately, I don't have a slide for it, but you may actually build it as with smaller subarrays or smaller arrays as multiple components and lay them out, right? In fact, that's how you reduce latency. You don't build a 1024 32-bit array. Maybe you build 10-word arrays and have 100 of them, and each of them may supply, I don't know, 1 bit, and you select the right ones. That's how you can actually simplify the design. I'm not going to go through this, but there are many, many ways of simplifying a larger array into smaller subarrays. Of course, this is the toy example because 10 is nothing, right? We're talking about terabytes and terabytes of memory. Clearly, you don't have 10 over there, right? Okay, so basically, in any type of memory, you have storage nodes in one column. They're connected to one bit line. And the address decoder over here activates one word line. This is the array structure, bit cell structure, if you will. You have word lines running horizontally, you have bit lines running vertically. And if you want to access one address, you access it one row at a time, or one word line at a time. Basically, you activate the word line. In this case, you supply the address 10, apply high voltage to it. That high voltage enables the stored bits that are connected to that word line to be connected to the bit lines. That's how you read the 3 bits that are on this word line. That's how you get 100. If you want to read word line 0, you supply address 00. This is clear, right? We've actually talked about row hammer effect and all of these things. They all activate the word line, if you will. So this should be hopefully simple. And basically, the access is controlled based on these switches. You have the access controlled by the word line. You activate the word line, and the cell gets connected to the bit line. That's the abstraction. That's actually true for DRAM, SRAM, flash memory, other types of memories, phase change memory, whatever memory you throw at me that operates based on electronic principles. In DRAM, for example, it looks like this. You have the word line, you activate it, this access transistor acts as a switch, it gets connected, it connects the capacitor to the bit line, and the capacitor, charge or discharge, causes a perturbation on the bit line, and the direction of that perturbation is detected by some sensing circuitry at the bottom over here. That sensing circuitry amplifies that perturbation and says, oh, you stored a 0 or 1. And this capacitor is really, 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 really small. The charge on it is extremely small. That's why you design it very carefully, and you have very little perturbation on the bit line. So you need to have a very strong sense amplifying circuitry to amplify that little charge perturbation. As a result, this is a really small circuit. The sense amplification circuitry, which happens to look kind of like that actually, is 100 times larger than this. So you can pack many, many DRAM cells in a single row and in a single array. SRAM, on the other hand, looks like this. This is the storage unit. It has a cross-coupled inverter, which we have seen before, which means that you have 4 transistors over there, right? And you have 2 access transistors over here. And when you enable the word line, these transistors act as switches. You have the bit line bar over here and bit line over here, and you do differential sensing at the output to figure out whether this was a 0 or 1. So you need some sensing circuitry to sense what is the data that you've stored is. We're not going to talk about that sensing circuitry as much in this course, but assume that it exists. It has to exist. And the sensing circuitry is different in DRAM, different in SRAM, different in flash memory, different in tape. Okay, so building larger memories requires larger memory arrays, clearly. Large means slow, but we don't want slow, right? So how do we make the memory large without making it very slow? I mean, if you make it large and it doesn't become slow, that's magic. Unless you move to a different technology. If you're in the same technology, and if you make it large and it doesn't become slow, then either your original design was not good enough, or there's some magic, which means that you should question the results. Usually, your access latency increases if your design was not inefficient. So the idea, if you would like to keep it as fast as possible, you need to use the idea that we've discussed before, which is banking. You divide the memory into smaller arrays and interconnect the arrays to the input and output buses. This is the idea of interleaving or banking. And large memories, all large memories are actually hierarchical structures like this. An array, ideally you want a 1 terabyte memory, but you don't want to design a 1 terabyte two-dimensional array. You chop it into 100 smaller arrays, right, equal size. Each of those 100 smaller arrays is still large. You chop it into 10 small arrays. Each of those 10 arrays is still large. You chop it into even 10 more arrays. Right? That's the idea. That's why this looks very hierarchical. For example, in DRAM, you have a channel, you have ranks, you have banks, you have banks are the things that are visible to the memory controller. You have subarrays that are currently not visible to the memory controller, but they will hopefully become visible if the industry gets its act together. And you have, even the subarrays are slow, we have mats that are smaller. Okay, so basically we have a general principle that we've seen before. This is the banking that was employed in Cray 1, right? It's also called interleaving. And we motivated it in a different way in Cray 1, right? We want to supply high throughput, so we want to get one word at a given time, and we cannot do it from a single monolithic array, unless we have many ports of the array. So we're going to have smaller pieces of the array. We're going to chop it into smaller pieces called banks. Well, a single monolithic array, as I said at that time, is also bad for access latency. So you kill 2 birds with a single stone, banking, by chopping that single monolithic array into smaller arrays. Basically, a single monolithic large array takes too long to access and doesn't enable multiple access in parallel. To reduce the latency of memory array access and enable multiple memory access in parallel, we divide a large array into multiple banks that can be accessed independently, either in the same cycle or in consecutive cycles. And we've discussed this when we talked about Cray 1's bank system. Clearly, each bank is smaller than the entire memory storage, and accesses to different banks can be overlapped. So there's a key issue which we have discussed at that time, and that key issue was how do you map data to different banks, right? I.e., how do you interleave data across banks? Let me give a quick overview of DRAM versus SRAM. I've actually said a lot of this, but this is going to be a quick overview before we start the next lecture. DRAM clearly uses a capacitor, and capacitor charge indicates stored value. That's the storage device. Whether the capacitor is charged or discharged indicates whether you have 1 or 0, and you have only 1 capacitor, and you need to have 1 access transistor. It's very compact. One problem is the capacitor leaks through this resistance conductance path, capacitance path, RC path, and DRAM cell loses charge over time, slowly, which means that you need to refresh the cell. That's why this is called dynamic memory. SRAM, on the other hand, we've also seen this is 2 cross-coupled inverters. You have a feedback path that enables the stored value to persist in the cell, not in the sense of persistence for non-volatility, but persist for a while as long as the power is connected. You have 4 transistors for storage over here and 2 transistors for access. Clearly now this has become large. But all of them operate based on the principle that we've said. We have a memory bank, it is organized this way, and it operates very similarly. Basically, supply an address, you have some most significant bits provide the row, and you activate the row. Once the row is activated, you get all the bits in the row, and then the least significant bits tell you which column or which fraction of the bits you select and send it out. And we've already seen the row decoders, we've already seen the registers, we've already seen the mux over here. This is a demultiplexer, this is a mux multiplexer selector. So you've seen all of the components actually, and that's a bank. You decode the row address, which drives the word line. Actually, that should be a single word line when you decode the word address. The selected bits drive the bit lines, all of them over here in the same row. Entire row is read. You amplify the data of the row, and the amplification is different depending on the technology. You decode the column address using the column decoder and select a subset of the row to send to the output. And then at the end of this, you need to pre-charge the bit line for next access to be able to determine what the value of the next access should be. Because in DRAM, for example, you need to ensure that the bit line is set to a reference voltage value, VDD, maximum voltage over 2 in most systems, such that you can determine whether the perturbation is positive or negative, right? And that's really important. You need to prepare the array for the next access after you're done with the access. So if you look at SRAM, it looks like this. It's very similar, as you can see. The way you decide N and M is you try to make it rectangular, each array rectangular, to minimize the overall latency of access. But this is the read sequence. You decode the address, you drive the row select, selected bit cells drive the bit lines, entire row. And differential sensing and column select amplify the data, and you pre-charge all the bit lines at the end. Access latency is dominated by how fast you can, basically decoding certainly, but also how fast, if your array is large enough, how fast you can drive the rows and how fast your bit lines actually can provide the data into the sense amplifiers. So there is a long access latency because of these. And how long it takes to do the next access, this is called the cycling time. You do one access, you want to do another access, that's called cycling time. That's dominated by steps 2, 3, 5, because 5 is important to get the array into the shape such that it's ready for the next access. You need to prepare the array. DRAM looks very similar, as you can see over here. In this case, SRAM, we supplied all the M plus M bits at the same time. Give me 1 second until I finish this. In this case, we supply the row address first and then the column address. You see that we have latches over here. This is because a DRAM chip is a separate chip, and you want to minimize the number of pins to the chip. And that's the idea. And the read sequence is very similar, as you can see, but there's flip-flopping sense amp. You have destructor reads, charge loss over time, and you need to refresh this. So we're going to pick up with the differences between DRAM and SRAM, but hopefully all of these are clear. But this is going to motivate the reason we develop memory hierarchies going forward, because we have different technologies to do different things and that are good at different things. Okay, I'll see you tomorrow.